Hey guys, sorry, Screencast-O-Matic will not let me use my webcam right now, still figuring it out, but I wanted to record the notes for section 6.8 anyway, which is on enthalpy of formation. So we've been talking about a lot of different enthalpies. So we talked about like bond enthalpies, which is basically the enthalpy or energy that's stored in bonds, and today we talked about enthalpy of formation, which is a different type of energy or a different type of enthalpy. So that's why you see like all these kind of different types of equations, but these are all methods to basically determine the same thing, which is enthalpy of a reaction. So we've looked at finding the enthalpy change of a reaction using calorimetry experiments. We've talked about it using bond enthalpies, and today we're talking about using enthalpies of formation. Later on, we're going to be talking about Hess's law, which is another method. So what is enthalpy of formation? It's basically a value that tells you how much energy is lost or gained during the formation of 1 mole of a compound from the most common form of its elements in their standard states. So you will see this delta H with a weird 0 and a weird F. That is the symbol for standard enthalpy of formation, and that is associated with a certain element or compound, well, really compound, that you will be using to basically determine the enthalpy of formation of a reaction. The little weird O thing up top, that means standard state, which means it has to be 25 degrees Celsius and 1 atmosphere. So this method can only be used if the system is at standard state, 25 degrees Celsius and 1 atmosphere. And the little F tells you formation. So we start with the elements and assemble every compound in the balanced chemical equation, and that's what gives us the enthalpy of formation. So we'll look at an example to see what that really looks like, and we're going to be looking at methanol. Methanol is based on the compound methane, CH4, but instead of one of those H's, the H is replaced with an OH group that makes it an alcohol, and all alcohols end in this OL. So methanol is a type of alcohol based on methane. So the chemical formula for methane is CH3OH. So it's made of carbon, hydrogen, and oxygen. So this enthalpy of formation, this delta H here that we find here, is based on this chemical equation. Carbon, in its standard state, 25 degrees Celsius and 1 atmosphere, is a solid, specifically graphite. Hydrogen and oxygen are both diatomic elements, so they're not just H and O. They have to be H2 and O2, because at the standard, under standard conditions, they are diatomic molecules, H2 and O2. We have a coefficient of 1/2 in front of O2, which looks kind of funky, but remember that the enthalpy of formation is for forming 1 mole of that product. So this enthalpy of formation for methanol, we just want 1 mole of methanol. Since methanol only has 1 O, but oxygen has a standard state of O2, we have to have a 1/2 coefficient in front of it. So that's why that looks a little bit funky. Here we have enthalpy of formation values for a few examples. For any element in its standard state, it's always going to be 0. So standard state for most metals is going to be a solid. So calcium solid, silver solid, sodium solid, iron would be solid, and its enthalpy of formation would be 0. But weird exceptions are like your diatomic elements, like O2, Cl2, N2. Since they are diatomic, they're not just O, Cl, H, N, they're O2, Cl2, H2, N2. And those have a standard enthalpy of formation of 0. The other states of those are not at standard state, so the enthalpy of formation would not be 0. Another example would be like ozone, O3, which is common under standard conditions, but O2 is more stable, more common, so that's why O2 is listed for that standard state, standard formation. Another weird example is like carbon. So carbon solid has a few typical ways to exist under standard conditions, so like diamond and graphite. Diamond and graphite both exist at 25 degrees Celsius and 1 atmosphere. Graphite is more stable than diamond is, so graphite is listed as a standard enthalpy formation of 0. The standard enthalpy of formation for a diamond is going to be 1.8. Siri's talking to me.
Okay, I found this on the web for is there anything information for?
Sorry about that. So the heat of formation or enthalpy of formation for diamond is going to be 1.88 kilojoules per mole, not 0. These are not values you necessarily have to memorize. I would memorize what these standard states of elements kind of look like know that oxygen is O2, not O. But usually a table will be given in terms of the problems that we'll be doing. If you look on page 1059 in your textbooks, which is Appendix C, the enthalpies of formations of certain molecules is listed there, so you can use that. The equation or formula we'll be using to calculate the enthalpy of reaction with these standard enthalpy of formations is equal to the sum of the heat of formation of the products minus the sum of the heat of formation of reactants. And each of those heat of formations do need to be multiplied by the stoichiometric coefficients that is found in that balanced chemical equation, because this does depend on the amount of product or reactant that you have. So this equation puts a negative sign in front of the sum of the heat of formation of reactants. This is done because reactants are not being formed, they're being broken apart. You're flipping the delta H of formation equations for the reactants, so you must also change the sign. If you put them together, if putting them together, forming them is exothermic, then blowing apart is going to be endothermic, it's going to take energy. The enthalpy of formation of reactant values have the same magnitudes, but opposite signs. For products, when we take those elements as they most commonly exist under standard conditions and put them all together, form the products of the overall chemical reaction, the step is exactly the same, so we don't need to change the sign. So the heat of enthalpy of products chemical equations are not being flipped, so we do not change the sign. So that's why we are subtracting reactants from products. Reactants we are taking apart, not putting together, so that's why this negative sign is there. Products are being put together, so their heat of formation sign does not need to change. Using this method, an overall reaction is thought of as being the enthalpy change that takes place when the reactants are blown apart into the most common forms of their elements under standard conditions and then reassembled into products. The heat of formation values are defined as being heat lost or gained when 1 mole of a compound is assembled from the most common forms of its elements, so that's why we have to multiply the heat of formation values by these stoichiometric coefficients in the balanced chemical equation. So if we are assembling 2 moles of water, then the value will double that which is given in the appendix in the back of your textbook. So here we have a few examples. We want to find the enthalpy of formation, the standard enthalpy of a reaction for the thermite reaction that is given above in blue under standard conditions. Oh, I did not format this correctly. That's fine. Little spoilers. So your heat of reaction is going to, again, be equal to the heat of formation of the products minus the sum of the heat of formation of the reactants, and of course multiplied by their coefficients. So for our products, we have 2 times the heat of formation of iron solid plus 1 times the heat of formation of aluminum oxide minus 2 times the heat of formation of aluminum solid plus 1 times the heat of formation of iron 3 oxide. Alumina and iron, hopefully you notice, those are in their standard states, so those enthalpies of formations are going to be equal to 0. For iron 3 oxide and aluminum oxide, you do have to look in the back of your textbook for those values. So those are given there and there accordingly. If you plug this into your calculator, you should get negative 847.6 kilojoules per mole. We have another example with some more spoilers. We want to find delta H of reaction for this reaction between hydrosulfuric acid and oxygen to form SO2 and 2H2O. So this is going to be basically the same process. We have this given equation. Our products are SO2 and H2O. Our reactants are H2S and O2. We have to apply all the stoichiometric coefficients, so each one of these is going to be multiplied by 2 or 3. So there's that kind of laid out there. If you go, the only thing here that is in its standard state is O2, so that will be 0. The rest you will need to go to the back of the textbooks to plug in. So here we have 2 times the heat of formation of SO2 plus 2 times heat of formation of water minus 2 times heat of formation of hydrosulfuric acid plus 3 times 0. The overall standard enthalpy of the reaction is negative 1037 kilojoules per mole. We could also kind of work this backwards to find the standard heat of formation for a given reactant or product. So in this case, we're looking for glucose, which is right here. So we will be using standard enthalpy of oxygen, enthalpy of formation for carbon dioxide, and enthalpy of formation for water in this reaction. So we're going to take products minus reactants. We're going to have kind of an X for the heat of formation of glucose, because that's what we're solving for, and we'll know the heat of formation of the reaction based on this delta H that is given here. So this is that kind of laid out, and this is rearranged to find the heat of formation of glucose, which here luckily is in 1 mole. So we're going to be subtracting the heat of formation of the reaction, which is right here. So if you plug in those numbers, go back to the textbook to find them, you should find these numbers, and you will get the heat of formation for glucose to be negative 1,260 kilojoules. This table shows the enthalpy of formation values for several metal oxides and the approximate dates that humans first started using the elemental forms of those metals. Gold was the first to be used. It exists in nature in its elemental form. It is the only metal in this list that requires an input of energy to convert it to its oxide, because it's an endothermic reaction. All the other metals in this list exist as oxides in nature, so humans had to transform those oxides into metals. So if you think of like tin or iron, those kind of rust easily. So that iron oxide is a rusted form of iron. How did they do this? Well, since the forward reactions are all exothermic, the reverse reactions are endothermic. So metal oxides must be heated in order to drive off the oxygen to produce elemental metals. Moving down the list, you can see that more energy is required to decompose these metal oxides. So as human cultures got better at basically making fires, ovens, furnaces, they developed the ability to decompose metal oxides with more negative enthalpy value formation. So basically, these tools allowed us to create more by the input of heat. The problem with producing iron solid is that burning hydrocarbons can't concentrate enough energy. So hydrocarbons are like, burning wood and things, to convert iron oxide to iron and oxygen. So later we will kind of examine a reaction that can produce elemental iron with less energy, which I think we actually went over, the thermite reaction. Beep, beep, beep. So here we were able to produce iron using less energy without using a hydrocarbon. So that's why it took so long to basically purify iron. Just a little fun fact, things to think about, why chemistry is important and all that fun stuff. So that is all for our notes. Let me know if you have any questions. There will be a worksheet posted on Classroom for you to use. Did any of that record? Where?